Hello students, in this video we'll discuss the turning vector of a curve in arc length parameter. Let's be given a curve gamma, an arc length parameter, then for a fixed S0 in R, we know that gamma dot of S0 is a unit vector because it's an arc length parameter. Therefore, this has to be equal to cosine of some theta 0 and then sine of some theta 0, right? I claim there is a smooth function theta of S such that what? Such that theta of S0 is theta 0 and gamma dot of S is the cosine of theta S, the sine of theta S, like this. Perfect. All right. So all I need to do is show you that this function exists, right? Now, when I say a smooth function, I'm assuming that gamma is smooth, okay? So it's not only a curve in arc length parameter, but it's a smooth curve. So I should be a little more precise and say that this curve gamma over here is smooth. Okay? Excellent. All right, so I just have to define this. So we know, proof, we write gamma, we can write gamma dot of S as a function A of S and then B of S, where A squared plus B squared is equal to 1. Okay, that's what it means to be a unit vector, an arc length parameter. Now, of course, I'm going to use a differential version of this as well at some point in this proof. So this implies, of course, that 2A dot plus 2b dot is equal to 0, which says that a dot is equal to the negative of bb dot. Hence, a dot is negative b dot, like so, right? So I'm going to use this relationship quite a lot in our proof. And so now I need to define what this function is going to be. What is my theta of S going to be? So our theta of S is going to be this function over here. So theta of S is going to be theta 0 plus the integral from S0 up to S of A S prime B S prime dot minus B S prime A dot S prime ds prime. Like so. Of course, we notice that this looks an awful lot like the derivative of the inverse tangent function, right? Because the derivative of the inverse tangent has this sort of structure. And I can always put a what down here. In the back of your mind, you should think of this as being what? Divided by A S prime squared plus B S prime squared. But what do we know about those quantities over there? Those are always equal to 1, right? So in other words, that genuinely is the derivative of inverse tangent of B over A, right? Okay, so what's the derivative of theta? So it's theta prime. So theta prime. So what I'd like to do now, let's compute theta dot first. So theta dot is equal to what? Theta dot is going to be of S, of course. Is going to be A of S, B dot of S, minus B of S, A dot of S. Okay? Since these functions A and B are smooth, so is theta. So theta is smooth. Okay? I'm going to suppress the of S and then do the calculation, the rest of the calculation formally. Now define a function omega of S to be A minus the cosine of theta. Again, I'm suppressing the S here, so there should be an A of S and cosine of theta of S. I'm just trying to conserve chalk because chalk is a very valuable commodity, right? Quantity squared plus B minus sine of theta, quantity squared, right? Okay, so if I FOIL this out, I'm going to have A squared plus B squared. That's going to be a 1. Cosine squared plus sine squared gives me a 1. So I get a factor of 2. So this is equal to 2 minus, and then the cross terms are going to be 2 times what? So over here, I'm going to have a 2a cosine theta, right? A cosine theta. And then over here, I'm going to have a 2b sine theta, right? So plus b sine theta. And I would like to show that this function omega is identically equal to 0. If omega is 0, that says that a is cosine and b is sine, and we're done, right? So in other words, if omega is 0, then we're done. Notice, of course, that omega of S0 is equal to 0, right? That's clear because when I plug in S0, that's the assumption of the problem, right? Over here, that is the initial configuration. Good. Okay. So what suffices to show now is I'm going to look at this function over here. I'm going to call this function over here psi of s, and it suffices to show that psi is identically equal to 1. Suffice to show, need to show that psi is identically equal to 1, right? Then we'll be done, okay? So let's do it. So what's psi prime, or psi dot? Psi dot is going to be a dot cosine of theta, plus b dot, or I'm putting primes and dots here, right? Dot sine theta, plus, let's do it like minus a sine theta, theta dot, and then plus b cosine theta, theta dot. Beautiful, okay? And so now I have to fill in what theta dot is. So this is going to be a dot cosine theta plus b dot sine theta minus a sine theta. And then what? And then a b dot minus b a dot, and then b cosine theta times the same thing. a b dot minus b a dot, like so. Great. Now let's gather the like terms over here. So what's going to happen? Over here, this term over here is going to be an a squared. So let's put out like this. So I'm going to have an a dot cosine theta plus b dot sine theta. And then minus a squared b dot sine theta. And then plus a dot b sine theta. Okay, and then I'm going to have a b, so I'll have it over here, we'll have a plus a b dot cosine theta, and then minus b squared a dot cosine theta, like that. Great, okay? Now let's look at the terms, and look at these terms carefully over here. So let's look at this term over here. So I have an a dot, and then I have a b squared, this term over here, that's a negative. And then I need another cosine term over here. Well, let's look at this term over here. So this term over here, this is a b, I have a bb dot, but bb dot is the same as what? bb dot is the same as negative a dot over here, right? So this term over here, let's be a little bit careful about this. So I need to have an a dot cosine theta, right? So I have an a dot cosine theta with b squared, and then I need an a dot over here, right? Well, what I can do is I can replace bb dot with what? I can replace bb dot with negative a dot. So this thing over here, I can replace this whole expression with negative a squared b dot, like that. Or, excuse me, I can replace this expression with negative a dot. And then what we have over here, we're going to have a negative a squared and a negative b squared and an a dot with a cosine of theta. Well, what's that going to simplify to? I know that a squared plus b squared is equal to 1. Since a squared plus b squared is equal to 1, this term over here and this term over here are going to cancel out with that term over here. And then analogously, what do we have? We have a b dot sine theta. Okay? Now look at this term over here. This is going to be a b dot sine theta. That's good. And this term over here is an a dot, right? So that a dot, I'm going to turn into what? I'm going to turn that into a negative b dot, and then a b sine theta, right? By our argument over here, right? And so now, of course, what happens? Now I'm going to have an a squared, and then a b squared. So a squared plus b squared is equal to 1. Then I have a negative b dot sine theta. So that's going to cancel out over here. So this expression is equal to 0. So psi dot's equal to 0. And that says that psi is constant, and that constant has to be equal to 1, right? So in other words, I've shown the derivative of something is equal to 0. That function is a constant, so psi is 1, and therefore this omega is identical to 0, and this implies that a of s is cosine theta s, and B of S is sine of theta S. And this function theta S is called the turning angle. So theta S is called the turning angle of the curve gamma. And in further videos, we're really going to sort of focus on this turning angle and figure out how the turning angle can give us geometric properties of the curve itself, right? So it's going to be essential to understand this turning angle in the study of the Gauss-Bonnet theorem in terms of how we integrate different curvatures, geodesic curvature relative to total curvature. So we'll see that in further videos. Thank you very much.